laboratory scale catalytic fixed and fluidized bed reactors in the oxidative coupling of methane. The authors are G. Boehmer, L. Lehman, and M. Baerns. And the paper will be presented by Manfred Baerns.
First of all, I want to thank the organizers of this session for inviting me and to present some results of our research work. I will talk today about the use of different laboratory scale reactors, and I will talk about their performance and about the performance of the catalysts that we use. In the past, we actually have concentrated on two types of catalysts. We started with the lead oxide catalyst on various supports, and I will speak today about a alumina-supported lead oxide catalyst. And then, secondly, I will speak about a sodium hydroxide, calcium oxide catalyst which has a high basicity and has better selectivities, exhibits better selectivities than the lead oxide catalyst. These are the two materials that we are using. It is the lead oxide, 36% on gamma alumina, and I am talking about two kinds of materials: granular material 63 to 200 micrometers and pellets of 2.7 by 3.6 millimeters. And the sodium hydroxide calcium oxide catalyst was granular material in the range of approximately 200 microns. The various catalytic reactors that we have used are summarized on these transparencies. It's first a non-isothermal fixed bed reactor with a diameter of 15 millimeters and a length of 80 millimeters. For the catalytic layer, the reactor itself was larger. And then we had what I call a isothermal micro-fixed bed reactor with an internal diameter of 9 millimeters, and the catalytic layer was approximately 50 millimeters. In these cases, the catalytic material was mostly diluted with quartz in order to obtain isothermal operation. And then thirdly, I will talk about results obtained in a fluidized bed reactor with a diameter of 5 millimeters and a total length of 2000 millimeters. Also, the catalytic layer again was only in the range of 10 centimeters. The overall reaction conditions that we applied were total pressure 1 bar, temperature range 600 to 800 centigrade. The oxygen conversion change between 20 and 100%, that's just a rough figure. And the methane to oxygen ratio was in general 9 to 10. In some cases it was also lower, as you will see. Now I will first start with the lead oxide catalyst supported by gamma alumina, and I will report on various results. First, I will start with the non-isothermal fixed bed reactor. There we have measured axial temperature profiles. We have measured the oxygen conversion and the selectivity as a function of the time of operation, the local change of the lead oxide content of the catalyst along the reactor axis, and finally I will give you some results on the ratio of ethylene to ethane as a function of the hotspot temperature in the reactor. Well, secondly, I will report on some results obtained with respect to deactivation in an isothermal fixed bed reactor. And then finally, I will report for this catalyst on results in the fluidized bed reactor, that's the selectivity as a function of the time of operation and of temperature. And then on the methane to oxygen ratio, and this is is a very interesting slide. I will give you some information about the axial concentration profiles within the fluidized bed reactor. Now I have to switch to the slides, or for one, at least to one slide. Okay, that's fine. Well, this is the temperature profile in the non-isothermal fixed bed reactor where we use pellets, lead oxide catalyst, and there are temperature profiles taken at different times of operation. We started after 4 hours, 24 hours, 80 hours, and 250 hours. And what we do see is that the hotspot temperature decreases with increasing time of reaction. Now this is an indication, of course, that the catalyst deactivates. And as you see, we have a rather high hotspot. We start with roughly 600 centigrade at the entrance, and it goes up over 800 centigrade at the start. Now, after this run, we have taken the catalyst out of the reactor and have analyzed it for its composition. And the results are shown in this transparency. Well, Z equals 0 is the entrance, and Z equal 4 centimeters. You will perhaps remember this. This was the position where we had the hot spot. And Z equal 8 centimeters was the end of the reactor. Now, the fresh catalyst had a bulk composition of roughly 38% of lead oxide, and now we do see that we have a concentration profile, that's bulk composition within the reactor. Now, at the lowest concentration we have, of course, there where the hot spot existed. Now, this is an indication that the lead oxide really is lost by the high temperature due to its vapor pressure. Now, we also have analyzed the phases of the catalyst. We started out with a fresh catalyst, that's a lead aluminate, PbAl2O4, with a little bit of PbO hexaalumina. But after the reaction, it turned out that most of it was the PbO6 hexaalumina, that's a spinel structure. And in this structure, the lead cations and the oxygen anions are rather mobile, and so we assume that this is really the active phase of the catalyst. And it was not only the outer shell of the catalyst particle, but also the core had the same composition. This was separately analyzed. So now we can turn on the slides, and I will stick to the slides. I think the power switch is not on. Thank you.
Tray all the way down. No.
It doesn't like your slides, man.
It's showing you
Foreign slides.
Projector is Japanese too.
That's the problem.
the expert.
Right, Tom? You're an engineer now?
So perhaps I can start already with the first one. Okay, that's fine. Well, these are the results obtained in the non-isothermal fixed bed reactor, which I just have shown you with respect to the temperature profile. The oxygen conversion stays constant for about almost 50 hours. It's 100%, but then it decreases, and after 250 hours we ever reached about 85%. The C2 plus selectivity decreases a little bit and stays then again constant at around 50%. The C2, the ethylene to ethane ratio stays more or less constant, and accordingly to the oxygen conversion, the methane conversion changes a little bit. Now, we also have looked at the ethylene to ethane ratio as a function of the hotspot temperature. And what we do see is that when the hotspot temperature is high, the ethylene to ethane ratio increases, which is certainly not surprising. But this, I think, is again an indication that we have a gas phase dehydrogenation of the ethane. Now, when we look at the deactivation behavior in a isothermal reactor, this was in a what I call a differentially operated reactor, we obtained the following figure. We have plotted the carbon dioxide, the rate of carbon dioxide formation and the rate of C2 formation versus time for different temperatures, 680, 720 and 760 centigrade. What we do see at the low temperature is that there is first a certain increase of the rate and then it levels out, and we assume that this is probably due to the formation of the active, catalytic active species, which I just mentioned, which we assume is the lead hexaalumina. The differential selectivity, that is the rate of carbon of C2 formation to the rate of methane consumption, stays constant within this range. But we know on the other side that and we have seen this in the previous slide, that the selectivity, the integral selectivity decreases, while the differential selectivity at the beginning of the reaction stays constant. That is this line. Now, the reason for this is certainly that the deactivated catalyst catalyzes the deep oxidation of the C2 hydrocarbons. And this is probably due to the effect of the alumina, which is not covered anymore by lead oxide. The alumina itself is a non-selective type of catalyst. I will now turn to results obtained in a fluidized bed reactor. to which we have applied a certain temperature program. The temperature is plotted on the right-hand side, and this is the temperature profile. Now, from time to time, we have re-established a reference temperature. The reference temperature was 690 centigrade, and we have measured the C2 plus selectivity, and these are the full symbols. And what you do see is that over the whole period of time, the C2 plus selectivity stays constant. I think that is the most important result which I want to derive from this figure. But when increasing the temperature, you can see that the C2 selectivity also increases, decreases the temperature, also decreases the selectivity. In the next slide, I want to show you the dependence of the C2 plus selectivity on the temperature measured in a fluidized bed reactor. The data have been obtained for two lead oxide catalysts which have been reproduced. So the triangles are the reproduction of the circles, and we do see that there is obviously an optimum temperature where we have a maximum in the selectivity, which is somewhere around 1050 to 1100 Kelvin. Well, and in this figure, I have plotted the C2 plus selectivity versus temperature again, but now for different ratios of methane to oxygen, 10, 6.5, 4.5, and what we do see is to be expected with higher methane concentration, the selectivity as compared to oxygen, the selectivity is higher than for the lower ratio, 4.5, that is the lower line, and the data 6.5 between. In the next slide, I want to show you the concentration profiles that we have measured within the fluidized bed reactor. Methane concentration and oxygen concentration. These are our reactants. And what we do see is that the oxygen is consumed very close to the distributor plate. That means that most of the catalytic of the fluidized bed material is just material which transports the heat. And so there is an excess of catalytic material available, and this is certainly the reason that we did not observe any deactivation of the lead oxide catalyst in the fluidized bed reactor. And the same you can see for the ethane and ethylene concentration. There is of course a small increase in ethylene concentration. The ethane concentration stays more or less constant, and this is probably due to some experimental errors that we don't see an increase in the ethane concentration. There should be a small decrease due to the increase in ethylene concentration. And again, the carbon dioxide concentration stays constant too. So this is the important result for the fluidized bed reactor, that we don't observe deactivation, but this is probably due to the excess of catalytic material in this reactor. Now I will turn to the sodium dioxide, calcium oxide catalyst, where we have operated a non-isothermal fixed bed reactor. Also the material was diluted with quartz granules. And when I say non-isothermal fixed bed reactor, this means that we had hot spots in the order of 10 to 20 centigrades, not as high as I reported for the lead oxide catalyst. But this was due to the dilution. The oxygen concentration Well, we have also applied a temperature program. We started with 720 centigrade, raised the temperature to 790 centigrade, and then decreased it again to 720 centigrade. And what we do see is that the oxygen concentration, which is a little bit below 100%, decreased to 100% when we increase the temperature. The selectivity increased from approximately 50% to roughly 70%, and then after 220 hours, when we decrease the temperature, we obtain more or less the same selectivity as we had before. That is to say that this catalyst didn't show any deactivation behavior. We also have looked in a fluidized bed reactor at this catalyst, and after an initial period of about 5 hours, we had a constant oxygen conversion. Also the C2 plus selectivity stayed constant. It's about 70%. And this ratio of ethylene to ethane stayed also after about 20 hours constant. And the same is true for the methane conversion. What I would like to mention is that the C2 plus selectivity of the same granular material that we obtained in the fluidized bed is higher than the one that we obtained under the same conditions, that means temperature and methane to oxygen ratio, as compared to the fixed bed reactor. And we believe, we have supported this belief by some calculations, that this is due to transport phenomena. As I explained yesterday already in the other session, we have bubbles flowing through the fluidized bed, mostly free of catalyst, and the gas has to diffuse out of the bubbles into the emulsion phase. And in the emulsion phase, in the bulk of the emulsion phase, the oxygen concentration is 0. So we have a gradient from the interface of the bubble to the emulsion phase, where we have an oxygen gradient. And that means that we have a lower oxygen concentration at the places where the reaction occurs than in the corresponding gas phase, in the catalyst-free bubble phase. In the next slide, I want to show again the selectivity as measured in the fluidized bed reactor as function of temperature. And again, it appears that there is a optimum temperature somewhere around 1050 to 1100 Kelvin. And in the next figure, I have compared the results for the sodium hydroxide calcium oxide catalyst. That's the upper curve. This curve belongs to the lead oxide. These are the data which we have seen before. And I have plotted also some data that we have obtained with the pure calcium oxide, which we have used as a catalyst. And this material has a lower selectivity than the sodium hydroxide calcium oxide catalyst. And this is certainly due to the fact that the calcium oxide impregnated with sodium hydroxide has a higher basicity than the calcium oxide itself. This supports again the assumption that high basicity is necessary for high selectivity. Now these are the results which I wanted to report to you about the different reactors. And I want to conclude with a final slide in which we have done some rough calculations how a large-scale reactor would behave. And so we have done some calculations for a non-isothermal fixed bed reactor, that is to say a multitubular fixed bed reactor, where the tubes are cooled by some cooling agent like a melt. Then we have done some calculations for a multi-stage adiabatic fixed bed reactor, and certainly for what I call a cross-flow reactor. That is to say, we have separated the adiabatic reactor in different stages, and between, as before, but between the stages we introduced oxygen in order to keep the oxygen constant, to achieve high methane conversions, but simultaneously keeping the oxygen concentration low. So not the total oxygen was introduced at the reactor inlet, but stage-wise. And then finally, we have done some simulation for a fluidized bed reactor. Now the data which I will show you in a moment just show a certain trend. The selectivities that we have calculated are a little bit too high, by about 10% as compared to what we have measured. But nevertheless, I think it's quite interesting to show what the results are. We get the slide. No, the next one.
Next one?
Yes, please. All right. We used a lead oxide alumina catalyst, temperature 1023 Kelvin. That's the entrance temperature. For the fluidized bed reactor, it's constant, but for the other reactors, it changes. Methane to oxygen ratio 10. That's the methane conversion. That's the selectivity, which is particularly for the fluidized bed too high. These are the corresponding yields. And here it should say space-time yield. It's tons of C2 hydrocarbons per cubic meter of catalyst per hour. Now what we do see is that the non-isothermal fixed bed reactor has the highest efficiency. Then we have the adiabatic fixed bed reactor multi-stage and the cross-flow adiabatic multi-stage fixed reactor, where we have about 1. And the fluidized bed reactor has surprisingly the lowest efficiency. But this is of course due to the fact, as you will remember, that most of the reaction occurs already very close to the bottom of the reactor, and the other material, the inventory of the catalyst, is not really used anymore, but it is needed as a heat transfer medium in order to keep the temperature constant. Well, by this I want to finish. Thank you very much.
Questions? I didn't catch how was your fluidized bed. Is it circulating or is it just bubbling?
It's a bubbling fluidized bed, yes.
Bubbling for the, what's the resistance?
The calculations were done for bubbling fluidized bed, yes.
What's the mechanical resistance of the sodium calcium oxide catalyst?
Well, we have operated the catalyst over about 200 hours, 240 hours, and during this time we didn't really have any significant loss of material. We had a cyclone within our fluidized bed so that the fines were put back into the fluidized bed, but there were no fines of such a size that they were elutriated.
Nothing below 5 microns?
Nothing below 100 to 50 microns. Insignificant amounts.
Because it's highly basic material that generally is not resistant to water and CO2, and it goes into powder very rapidly.
Yes, but I think the point is that we are working at rather high temperature, and we have calcined the material before we used it. So this may help in stabilizing its mechanical resistance. But I agree, in order to use it for a commercial or a pilot plant reactor, one certainly has to do some more experiments in order to test its mechanical long-time stability.
In a fluidized bed, is sodium and calcium oxide better than lithium and magnesium oxide, better than something else?
I cannot answer this question because we haven't made the experiments.
Have you tested other catalysts in a fluidized bed that you didn't present today? Just out of curiosity.
In fact, no materials which were significantly different from those which I recall.